Welcome to By Excellence Tutorials. And if you have not yet subscribed to the YouTube channel, kindly subscribe and make sure that you click on the notification bell so that you get notified each time a new video is uploaded. And here you'll never go wrong. Okay, so in this video, we are going to look at Doppler effect. But before we go to doing Doppler effect, I want us to, if you watched the previous video where I had a session with students, we are going to discover that there is a question that was cut whilst we were solving. Okay, so we just solved for A and we did not solve for B. So before we go into Doppler effect, I would want us to finish what we started. Okay, so now a small source emits sound waves with a power of 80 watts. What is the intensity? 3 meters from the source, so we solved that one. And then B says, at what distance the intensity be 1/4 as much as it is at R being equal to 3 meters. Okay, so what it is let the intensity at 1/4 of radius 3 meters be I1, or maybe I put this to be I1, okay, subscript 1, and then let me put this to be I, okay, and this intensity we are told that is 1/4 of I1. So we have 1/4 of 0.707 watts per square meter. So what we're going to have intensity to be 0.17675 watts per square meter. So this is the intensity at this is 1/4 of the intensity. So now we want to find the radius, we want to find the distance. At what distance? Okay, so now we have intensity being equal to energy squared. So we make R the subject of the formula, of which is going to give us R squared being equal to 4 pi. Yeah, so R is actually going to be root of power, which is 80 watts, and then we have 4 pi, and the intensity, this intensity that we have just found, okay, which is 0.17675. Okay, and this is going to give us 6 meters. So the radius is going to be 6 meters here. So that's how we solve that one. And for C now, we have been asked to find the distance at which the sound level is 40 decibels. Okay, so now I think on this one, I'd want to explain something concerning spherical waves. Okay, because it's that concept that we're going to try to use here. So in simple terms, if you have a source, like in this case, we have a source, a small source. Okay, we have a small source. So let me illustrate this in this way. Okay. Hope you're seeing what is happening. So if you have a small spherical object, and this object is oscillating, okay, this object is oscillating in a way that its radius is changing periodically. Okay, changing periodically with time. Okay, so we have rays coming out. Okay, so if you have a small spherical object that is oscillating, so that the radius is changing periodically with time, it's going to produce spherical waves. Or spherical waves are going to be produced, or that's how spherical waves get to be produced. Is out of a small source, a spherical source, of course, that is oscillating in a way that the change in radius is periodically with time. It's periodic with time. You are going to produce a spherical wave. Now, another thing that it is, these rays that you've seen I've drawn, they are coming out, okay, outward, and they are moving at constant speed. The speed at which these rays are moving is constant. And if those two cases are satisfied, that the radius of this source is changing periodically, and the speed at which these rays are moving outward is constant, and that a spherical wave is produced, what it is that it is concluded that the energy, okay, the energy propagated is equal. Okay, the energy that is propagated here is equal, is distributed equally at any point in all directions. It is propagated equally. Okay, so now we may have here, okay, radius 1, and then we can also have here radius 2. You can see that we have different, so these are called wave fronts. Okay, these are called wave fronts. So you can see that our radius 2 is greater than radius 1. So if we are to write the intensities, okay, of these points in this spherical surface, okay, or spherical wave that is produced, we are going to have, for R1, what we're going to have is intensity 1 is equal to power the average. We've said that the power is the same. Energy produced or propagated is equal in all the directions. So we have the average power over the area, and this area we have one like that. Okay, and then for R2 at this point, we're going to have intensity 2 being equal to power average and area. And this is R2. Okay, so if we have these two intensities, we can easily get the ratio of those two intensities and the radius. Okay, we can get the ratio. So we can divide I1, I2, and then we're going to have average for, okay, and then we are dividing just for the sake of those who may have difficult with algebra. Yeah, and then here we are going to have power squared. Okay, and then we introduce a multiplication sign. The numerator goes on the denominator, and the denominator goes on the numerator. Like that. So energy is the same. So what we're going to have is this, and that will cancel this, and that will cancel. And remember, here we have the ratio of these intensities. So what we're going to have is the ratio of intensities to actually R2 squared over R1 squared. Okay. So this ratio of intensities at two spherical surfaces, it's not only in sound. It cannot only be found in sound. You can also find it even in other waves, electromagnetic waves, light waves. You have this ratio of intensity. So that's how a spherical wave is produced. Okay. Yeah. So now we can solve, I think, question C. Find the distance at which the sound level is 40 decibels. So now we need to find so we have intensity 1, so we can find the intensity, the second intensity, okay, of which we know that the first intensity is at a radius or at a distance of 3 meters. Is at a distance of 3 meters. So now we need to find the distance where the intensity level is going to be 40 decibel. So we can use this 40 decibel to find the intensity, because we don't have the intensity. What's the intensity? When we have the intensity level of 40 decibels. So what we have is, remember the equation we've been using in the previous videos, where we have decibel level, it's actually 10 log intensity over threshold of hearing. Okay, so the decibel level here is 40 decibel, and we have 10 log. We are looking for this intensity, so we're going to put a 2 there to differentiate those two intensities that we've done. And then the threshold of hearing, we know that is 1 by 10 to the power 12 watts per square meter. Okay, so we divide both sides by 10. Okay, and then we are going to have okay, right here, we're going to have 4 equal to log of I2 over 1 times 10 power negative 2 watt a square section. So I believe you still remember about logs. So this log, it doesn't have any symbol here, means that that log is to the base of 10. So if that log is the base of 10, it can be written, okay, in index form as the base of 10, the power 4, being equal to so if you've gotten lost, go and check something on logs. Actually, the laws of logs, or how to solve these logs. So here you're going to see that we have intensity 2 to be and multiplying by 10 to the power 4, like that. So our second intensity is going to be 1 by 10. Okay, so there you can just more like add the powers, and then we're going to have -8 watt per square meter. So this is the intensity at that distance that we're looking for. Okay, so now since we can use this we can use this ratio to find the radius now, since we have 3 known factors now. Okay, so we have intensity 1 over intensity 2 being equal to R and R1. That's okay. So intensity 1 is actually 0.707. Okay, intensity 2 is 1 by 10 to the power -8. And then we have radius 2 is the one that we are looking for, and radius 1 is actually 3, so 3 squared. Okay, so if we do the multiplication, we are going to have radius 2 being equal to 0.707 by 9, okay, divide by 1 by 10 to the power -8. Okay, so just 2. Okay, the second radius, we are going just to square that. Okay, so we're going to have a root of 63. Okay, so square root of that, we get R2 being equal to 224.98761 meters. Or you can write it to be 2.52 times 10 to the power 4 meters. And so that will be the distance. Okay, so now we can go and do what we want to do now. Okay. So I want you to now think about a situation. Obviously, you've been there, where you are maybe standing along the roadside, and then there is maybe a motorcade. Okay, the president is passing, the minister is passing, or any high official is passing. They usually move with the police escort. So if you're standing, and then you hear the siren, it may not only be that, it also may be the ambulance. Okay, you're standing along the roadside or somewhere near, and then you hear the siren approaching you, and then the time it will approach you, it will proceed, okay, moving in the direction where it is moving. So now there'll be actually a change in sound pitch, actually the frequency, the pitch, as it was coming near you and as it is going away from you. Okay, are you now trying to relate? The ambulance is coming, and the way you'll be hearing the sound to be like the pitch will be increasing as it is coming towards you. Okay, and sometimes you may even close your ears to say, no, this sound is too much. But compared when it was far, the sound was more like faint. So the pitch of the sound is increasing, not more like, it's more like, okay, yeah, it's more like increasing as it is coming near you. And then as it is going away from you, you're going to see that the sound will be getting faint until you stop maybe hearing that sound. If it is going far away from you, if the distance becomes greater than you. Now, what is that phenomenon? Get it? So that phenomenon now is what we refer to as Doppler effect. Okay, so we're dealing with Doppler effect here. Doppler effect. So these are the scenarios. Sometimes you just hear, but you don't know what it's all about. Okay. So when we're talking about Doppler effect, I've just explained what Doppler effect is. So when we're talking about Doppler effect, it's actually a phenomenon. Okay. It's the phenomenon of change in apparent pitch of sound. Okay. Due to relative motion between the source of sound and the observer. So the source of sound, observer. So the source of sound here is the ambulance. It's the source of sound. And you as a human being who is standing there, you are an observer. So now, the change in apparent pitch, okay, of sound due to the relative motion. So sometimes you may also be moving. I've just given an illustration where you are standing, okay, you are stationary. Okay, but also the observer can also be moving. So those are cases that we're going to look at as we are trying to derive now the equations that will govern, okay, this Doppler effect. So we have different cases where the source is moving, and also maybe the source is moving towards the observer whilst the observer is stationary, or the source is moving away from the observer whilst the observer is stationary, or both are moving towards each other or away from each other. Okay, so we have those cases. Now, when we're dealing with Doppler effect, we need to make assumptions before we begin to derive. We need to make assumptions, and one of the assumptions is that okay, we need to make an assumption. Someone was like, wow, physics is all about assuming something is not. Okay, so we make an assumption that the air is stationary. Okay, let's make an assumption that the air is stationary. Okay, and the speeds and all speeds measurements are made relative to this stationary medium. We know that air is a medium which sound, propagated. Okay, so that's an assumption that we have when dealing with the Doppler effect. So the air is stationary, and all the speed that we're going to measure are made relative to this same stationary medium. Okay, so now we are going to take also taking V naught, okay, not really V naught, or VO. This is going to be the speed of the observer. Okay, so that O means observer, and then we have Vs, and this is going to be the speed of the source. Then we have V as the speed of sound. Okay, so we have those, and then we can also have, okay, so this is the frequency of observer. Okay, so we also have that is frequency of the source. So we have the wavelength of the source as well. So you know what these will be meaning as we are deriving here. Okay. So our first case is when the observer is moving relative to the stationary source. Okay, so case one. Observer relative to a stationary source. So the observer is moving relative to the stationary source. So we have okay, we say you are going to the hospital. Okay, you are going to the hospital. So we have the source here, and then we have the observer there. Okay, so we have the source. The observer is moving with the with the velocity like that. Now you're going to the hospital, you are entering the gate of the hospital, and there was a patient, an emergency that was brought by the ambulance. So the ambulance is there just reaching, and you are also has reached, and you are entering the gate. So the ambulance is stationary, but maybe the driver has forgotten. So we're making an assumption that the driver has forgotten to switch off the siren. So the siren is just ringing, you understand? It's ringing, the siren is making noise, and you are approaching. So this is the scenario. So you're approaching. What will happen? How will be the pitch? How will be the change of the speech? How it will be the Doppler effect? Okay, this is what we're trying to do here. Okay, so now this source is stationary. So the velocity is actually 0, like that. And then sound is moving to reach you here as you are coming. So there's that V at the speed of sound. And also these wave fronts, these are also wave fronts. Okay, the wave fronts are also from one wavefront to another wavefront. We have that distance, and that distance between these two wavefronts is the wavelength that we have of the source. Okay, so we take the frequency of the source to be Fs as the frequency of the source, and then we also take this as the wavelength of the source. Okay, so now, so when stationary, what we're going to have, okay, the observer, the velocity of the observer and the velocity of the source will be 0. And what will be the frequency that, or what will be the wavefronts that is going to be detected by the observer if is stationary, if the velocity is 0? We are going to see that the observer is going to detect, let me say, detected wavefronts. These are wavefronts. You get it? These are wavefronts. Wavefronts. Okay. Will be Okay. So this is wavefront per second. Okay. When it's the observer is stationary and the source is stationary as well, the observer will detect the frequency of the source. Okay, and this can be written in this way. Of the source. But now when the observer begins to move, so here the frequency of the source, when they are stationary, the observer and the source, the frequency of the source is going to be equal to the frequency of the observer. Okay, so now when the observer begins to move, okay, begins to move towards the source, what we're going to have is that this observer is going to detect an addition wavefronts as he will be moving in this direction. So now when he's moving in this direction, he's going to cover a certain distance. Okay, so since he's moving at a speed v naught, the distance which is going to be covered in time t is v naught times t. Okay, in time t seconds. And in this time, in this interval of time, is going to detect the wavefronts, okay, which will be over that. Okay, now the wavefront per second, meaning we're going to get the wavefront per second, since this is the wavefront that is going to detect now after covering a distance of v naught t. Okay, so now the wavefront per second wavefront per second is actually going to be t, and those t's will go, so we have v naught over that. Okay, so what we're going to have now, the frequency that is going to be heard by the observer is going to increase. Okay, where we have so this fs is actually the first one. Okay, it's more like the initial state. So we have the frequency of the observer, frequency of the source, plus this wavefront. This is the wavefront at the beginning, plus the wavefront per second. Okay, after this observer begins to move towards the source. So we get this equation here, and we place, excuse me, and we place it in this equation where we have fs plus v naught over, we have v over fs, like that. And then what we're going to have is okay, plus what we have v naught fs over v, like that. Okay, so we can simplify this where we have v, and then there we're going to have v fs plus v naught fs, and then we can factor out. So some they do it direct and they fail to get the derivation correct, and they begin to wonder, say, what's happening? So we factor out fs, and then we have v plus v naught over v. and this is going to be the change in the pitch. Okay. When the observer is moving towards the source, or a stationary source, in fact, this is going to be the change in the pitch. So like I mentioned, to say there are different cases. So this one, you can see that as the observer is moving towards the stationary source, is going to detect an increase in frequency. Okay, the frequency is going to increase. Now, when the observer is moving away from a stationary source, you will see that the frequency, even logically, the frequency is going to reduce. It's going to decrease until you stop hearing the sound. So what it is you use the same steps that we've used. Okay, you use the same steps that we've used, but so I'm saying when the observer is moving away from the stationary source. You're just going to have a negative of the velocity of the observer. So the detected frequency is going to reduce and is going to be given by this. Also, we will have a minus here. So you use the same procedure to find this equation. So we're going to go to case 2. And therefore, case 2 is that one that I had illustrated first. Okay, when I was introducing this, and I talked about the ambulance coming and you're standing around the roadside or whatever. So case 2 is when the source is moving relative to a stationary observer. Okay. So the observer is stationary and the source is the one that is moving here. So check this out. The source is moving towards the observer and the observer is stationary. So what you're going to discover is that you've seen the wave fronts, the way I've drawn the wave fronts, the distances is reducing. Okay, they are becoming like the wave fronts passing this observer are closer together. Okay, are close together because of the source going towards the stationary observer. Okay, so now this wave front of observer. Okay, let me put. So we have the wave front of the observer, and then we also have the wave front of the source. Okay, we have the wavefront of the observer and the wavefront of the source. And what you're going to see is that the wavefront of the observer is shorter than the wavefront of the source. Okay, it's that thing whereby you know the relationship between the frequency and wavelength. Okay, you know the relationship. So when this frequency is high, the wavelength will be small. So the frequency as the source is coming towards the observer will be increasing. The pitch will be more like increasing. You'll be hearing more sound, a lot of sound. So the wavelength now is going to be shorter. So the wavelength of the observer is going to be shorter than the wavelength of the source. So now if we take this source moving a distance, okay, so the source is moving with a speed vs, and then as it is moving at that vs in a time period t, okay, in a time period t, the distance that is going to be covered by the source on each period is going to be what? Is going to be st. This is going to be the distance. Okay, now if this is the distance, we know that period, this is period, okay, t is period, the time period. So we know that we have vs of frequency of the source. That since we know the relationship between period and frequency, is that relationship that we have, so we can write that in that manner. Okay, so we have that distance now means that the wavelength of the observer is going to be the wavelength of the source minus s over s. So this is actually relative motion. Okay, this is actually relative motion, where we have now the wavefronts detected by the observer. And then we have also the wavefront of the source minus this wavefront, whereby we have now the source that begins to move, the distance that is going to be covered by the source, and what will be the detected wavefront. Okay, so now this is what we have, and we know that we have the frequency that is going to be detected by the observer is, sorry, frequency by the observer that so we can substitute now that equation there, where we have the so substituting for that, we have source, so we substitute in this equation. Just like that. So it's a step by step. So here, f source like that, and then we're going to have that. Okay. Where we are going to have fsv over v minus vs. Okay. So frequency of the observer is going to be, we factor out fs, and then we have s. Okay, so this is when the source is moving towards the stationary observer. When the source is moving towards the stationary observer, we see that the frequency is going to increase here. Okay, because we have a difference at the bottom here. So if we have a difference and the velocity of the source is increasing, the speed of the source is increasing, we're going to have an increase in the detected or observed frequency there. Okay, as it is moving towards the source. So also the opposite of it is when the source is moving away from the stationary observer or from the observer who is at rest. So when the source is moving away from the observer at rest, it's just going to be the opposite of that, where here now this is no longer going to be the difference. Sorry. This is no longer going to be the difference, but it's going to be the sum, and the observed frequency is going to be V over plus S. So the observed frequency is going to reduce as they expected. The frequency is going to reduce. Okay. So we also have a general case. Okay, a general case that which covers all the cases, I think. Yeah. So it can also be derived using two equations. I think this last one, and is it the last one? The second last and the other equation that we've derived are the ones that I used to derive that. So the general case we have a general case. We have the observed frequency being equal to so you can look at the values or what you've been told in the question and be able to plug in, and you're going to discover that some are going to be zeros, and this general equation can reduce to any of the above equations that have been derived. That's the beauty about this equation. Okay, it can reduce to any according to the condition that has just been given. Okay, so that is the general case, and that is about the Doppler effect. Okay, we can solve maybe one example on Doppler effect. So a train moving at a speed of 40 meters per second sounds its whistle, which has a frequency of 5 by 10 to the power 2 hertz. Determine the frequency heard by a stationary observer as the train approaches the observer. The ambient temperature is 24 degrees Celsius. Okay, so here we have the speed of the source, we have the frequency of the source, and we want the frequency of the observer, but we don't have the speed of sound. But we've been given temperature, ambient temperature, to be 24 degrees Celsius. So we remember we have to recall that formula as we're dealing with sound waves. Yeah, when we just started sound wave, we dealt with this formula. I think that has to be 331, I believe, over 273K. So this is the speed of temperature. Speed can be affected by temperature. Okay, so what we're going to have is so we convert 24 degrees Celsius to kelvins, and then we have 297K over 273K. So the speed of sound in that air is 345.2 meter per second. Okay, so we substitute. So the frequency heard by the observer is going to be, so we have 5 by, okay, sorry, we have 5 by 10 to the power 2 hertz. And then we have 345.2 meter per second over 345.2 minus 40 meter per second. Okay, so the frequency okay, so the frequency is going to be 565.5 hertz or 5.66 times 10 to the power 2 hertz. So this is how you can use Doppler effect, or you can apply Doppler effect in this way, and you can solve questions with those equations that we have derived. Okay, so I think before I go, I can even touch somewhere on shock waves. Okay, I'll just say something on shock waves. So shock waves are actually waves that are produced when the source speed, okay, the source speed exceeds the speed of the wave, or the velocity of wave velocity. Okay, that's when you produce a shock speed. For example, we have a boat. When you have a boat on the river, okay, so you're moving, you're cruising at a high speed. What's going to happen is that as you're cruising on the water, you see that you will be leaving something like this, and this is the boat that is going in this direction. Water will be separating like this, leaving some sort of a triangle, like, you understand? So now this is happening because of these are shock waves. So the waves of the water are moving slower than the speed. I mean, the speed of the waves of the water are moving slower than the speed of the boat. Okay, so the boat is moving at a high speed. That is why you are going to have that. You are going to be leaving this kind of shape behind as you are moving. Obviously, you have seen this. So this is an example of shock waves. And then when you also look at the the jet. Okay, you take for instance a jet. Sometimes you've seen fogs. So that fog that is formed is because of the shock. Is an example of shock waves. The speed of the jet is faster than the speed of the medium. Okay, so that is about the shock waves. And then also we have also um, interference. Interference of sound wave. I think when we're starting waves, in fact, when we just started in sound waves, we dealt also with the interference of waves. And I remember we talked about two kinds of interference. We talked about the constructive interference and also destructive interference. Okay. So when you are, for you to have a constructive interference, okay, I believe you still remember about interference. So interference actually is where you have two waves or two or more waves, okay, that are moving, and the wave that is going to be produced when you add these two waves of the same, is it frequency? Okay, it's either going to be a constructive wave or a destructive. It's going to be destroyed or it's going to be constructed. And in a constructive interference is where you have a wave being produced, which is have maybe an amplitude higher than the individual waves. And this constructive interference can only happen when the crest of the crests of these two waves are able to meet, and the troughs are also able to meet. So, but when the crest meets the trough of another wave, you're going to have a destructive interference. It's either the wave is going to be there, or it's not going to be there, or it's going to be there but with a small amplitude, more like destroyed. Okay, I don't want to go any much further on this one, but what we have is actually I can refer you to the previous videos about where you're going to find something about interference. Okay, I think I've done a video on that. So what we are saying is, so I'm not drawing correctly, but when we have the crest and the crest, if they meet, and the trough and the trough, they meet like this, you're going to have a constructive interference. A wave may look even like that. But if the crest is meeting the trough, you're going to have a destructive interference. So under constructive interference of sound here, we can talk about, maybe you have I don't want to explain this, but the situation is forcing me to explain a bit about this. Okay, let's do this. So if you have a sound, because here we're talking about interference of sound, of course, sound wave. So if we have one source, okay, one source here of sound, okay, So the illustration cannot be that good. Okay, but what I want is we have R1 and R2 there. So what it is if you have maybe a speaker here, okay, the source of sound, and sound enters here, okay, sound enters here. When sound enters and reaches this part, you're going to see that this sound is going to divide. The other sound will go this way and the other sound will go this way. Okay, so when it comes, it reaches here, it will have to combine again. It has to recombine. So when it recombines, the sound that you hear here, it will either be constructive or destructive. Okay, to either be constructive or destructive, provided that if these distances are the same, you are going to have a constructive outcome, constructive wave of sound, kind of wave that is going to come out here. And now here, you can even have to, you can calculate the path difference, path length difference, and for constructive, okay, so here, constructive interference, path length difference is given by that, where n is 0, 1, 2, and so on. Okay, but for destructive interference, you have the path length difference of n plus half. Also, n is starts from 0, 1, 2, and so on, like that. So that's a bit about interference of sound waves. I thought I was not going to do that in the next videos, so I thought of doing it right in this video. Okay, though it's not very much clear, but I believe you have an idea. Okay, so thank you so much for watching. Make sure if you have found this video to be helpful, useful, kindly invite many, send them the link so that they are able as well to benefit. And you can also comment, and we'll really appreciate. Thank you so much for watching. See you next time.